We have talked about general second order systems. General second order systems are characterized by two parameters, damping ratio and natural frequency. And looking at the value of damping ratio, we can qualitatively describe about the behavior of the system, transient behavior of the system. So if zeta is between 0 and 1, the shape of the response is underdamped. This is time axis, and a response of the system, step response. Laplace transform of the step response is obtained by multiplying the transfer function with the Laplace transform of the input. That is, and you remember our discussion on first order systems, and first order systems were characterized by single transient response characteristic, that was the speed of the response. And we were able to describe speed of response using different parameters, that is the rise time, settling time, and so on. For second order systems, there are two characteristics, that is the speed of the response and overshoot. Overshoot is the value, this is the steady state value of the response, and you can see that response first crosses the steady state value, and then after transients settles down to the steady state value. This is called overshoot, right? So the transient characteristics of second order systems are described by these things, overshoot. And the speed of response. Speed of response is can be described in terms of peak time. Peak time is the time at which response reaches its peak value, and it can also be characterized in terms of settling time. Settling time is the time when response settles down. So what do you think is the time when the transients will die out? Infinity. Theoretically, transients will die out at time equal to infinity, but practically, when the response enters into this band, then we say that the response has settled down. The time when response enters into this band and then stays inside that band, that time is called the settling time. From this graph, this is the time when the response has entered into this band and then it stayed inside this band. So this time is called the settling time. This band, what is this band? Generally, different people take it differently, but in our course, we shall take it the plus minus 2% of steady state value. That is, this value is 0.98 and this value is 1.02. 2% of the steady state value is this band. Another parameter, another specification that can be utilized to describe the speed of response is the rise time. How do we define rise time? It is the time for the response to rise from 10% of its steady state value to 90% of its steady state value. So this time is rise time. And in today's lecture, we shall represent all these specifications in terms of system parameters, that is in terms of zeta and omega n. So we start with the peak time. How we can determine peak time? Correct. So we can see from this curve that the derivative of this curve at this point, at this point, at this point, and so on, that is 0. So we shall simply obtain the derivative of this curve. We know the expression for this curve. What is that expression? We had obtained it. So C of t was described by 1 minus zeta square. We have derived this expression in the last lecture. If we take the derivative of this expression with respect to time, we shall get all these points. So which point will be the peak time? Maximum we get at all these points. This point, this point. Maximum by definition is the point where slope is 0. So at this point, so this is the second point at which we get maximum. So we shall take derivative of this curve with respect to time. We can take its derivative, that is easy, but we shall opt relatively more easier approach. That is, what is its representation in Laplace domain is given by this expression. This and this are the same. This is in time domain, this is in Laplace domain. So you remember that Laplace transform of c dot of t, derivative of c with respect to time, if we take its Laplace transform, what is that? That is equal to s multiplied by c of s, and c of s is over here, and this is omega n square s square plus 2 zeta omega n s plus omega n square. Clear? We have taken the derivative in Laplace domain. Why? It was easier for us. We could have proceeded in the same way. We could have taken the derivative of this expression with respect to time. But now we want it in time domain. What we can do? We can take inverse Laplace transform. And we have already learned the technique how we can obtain its inverse Laplace transform. Partial fraction expansion, or bring it into this form. For example, this had inverse Laplace transform of e raised to the power minus at sine omega t, right? So in the last lecture we also learned how to represent this denominator into this form. So you can represent it and then take the inverse Laplace transform. So that is given by this expression and this expression are the same. Omega n square, so omega n into omega n is omega n square. This term we have multiplied it over here and divided it. Here we have, if we expand it, this is s square plus 2 zeta omega n s plus zeta square omega n square. So zeta square omega n square is extra over here, which is subtracted from this expression as well, right? And now we can easily obtain its inverse Laplace transform. That is c dot of t, that is equal to omega n 1 minus zeta square e raised to the power minus zeta omega n t, and sine of omega n 1 minus zeta square into t. Is it clear? And at t equal to peak time, what is that? This derivative at this peak time is equal to 0. So this expression, this is some constant, so it is not equal to 0. So it means that this is equal to 0. So it means that either this is equal to 0 or this is equal to 0. When is this term equal to 0? At t equal to infinity, this term is equal to 0. So we are not interested in that time, the time at infinity. We are interested in this time. So we have sine of omega n 1 minus zeta square at tp, that is equal to 0. At what values of this sign is 0? 0, pi, 2 pi, and so on. We are not interested in this point. We are not interested in this point. This corresponds to this expression equal to 2 pi. We have this point, that is pi. And therefore, we have an expression for peak time, which is given by pi over omega n 1 minus zeta square. So peak time, the time at which the response reaches its peak value, is given by this expression. Any question up to this point? How we can obtain the peak value of this response. Peak value of the response. Substitute this value of time into the expression for this response. We get the peak value of response. So that is substituted over here. In one of our previous lectures, we had also represented C of t into this form. So we simply substitute t equal to Tp in this expression. So we have 1 minus e raised to the power minus zeta omega n. What is Tp? Tp was given by pi over, so pi over omega n 1 minus zeta square under root multiplied by cosine of omega n j. This will be cancelled out, and what will be that? Pi. And here is also sine of pi. Is it clear? So what is sine of pi? Sine of pi is 0. Cosine of pi is minus 1. So peak value of the response is, this is the peak value of the response. Peak value of the response is obtained by substituting t equal to Tp into the expression for C of t that is given by this relation. What is steady state value of this expression? Steady state value, this decaying term will die out, so steady state value is 1. So what is overshoot?
1 plus
Overshoot is this value minus 1. Overshoot is the peak value minus the steady state value. So overshoot is equal to e raised to the power minus zeta pi whole divided by 1 minus zeta square root. Is it true? So that is the overshoot. In terms of zeta, we have computed it. Sometimes we are more interested in percent overshoot. In that case, we have to multiply it by 100 and then we shall get the percent overshoot. Clear? Any question up to this point? You may sometimes like to rearrange it to write in this form. Take a natural log of both sides and then rearrange the terms. You have zeta in terms of overshoot. Clear?
Yes.
So we have talked about peak time, we have talked about overshoot. Next we talk about the settling time. The settling time is the time when response settles down. So how we can determine that time? There may be several different approaches. The approach that we follow is the simplest one. What is this graph? This is graph of only this term without 1, right? So as far as shape is concerned, it has the same shape as the this curve, right? So if this value is 0, this value is 0, and if I sketch the same band over here, you will find that the time when this graph enters into this band is the same time when this graph enters into this band. Again, this value is 0.02 and this value is minus 0.02. Is it clear? One more observation. One more observation is over here. What is plot of this curve? This function? Sinusoid. And what is plot of this function? Decaying exponential. This decaying exponential, if I plot it, it makes an envelope. So this is the envelope, right? So you can see that from this graph, the time when this envelope enters into this band is approximately the same time when this curve enters into the band. Clear? Or alternately, we can say that when this envelope enters into the band and stays into the band, this curve will definitely enter into the band and will stay into the band. Is it clear?
Yes.
So it means that instead of finding the settling time from this function, we find the settling time from this envelope, and the expression for envelope is, so at t equal to settling time, what is this value? So we can take equal to 0.2, 0.02, and then we have an expression for settling time. And what is that expression? We bring it to the other side and then rearrange it. So we have, what we have done is we have simply rearranged the terms. We have taken this term to the right hand side, taken the natural log of both the sides, and then finally we obtained an expression for settling time. So this expression can be utilized to compute the settling time, the time required for the response to settle down. However, this expression is quite complex. And what information does this settling time give us? It gives us the information about the speed of response, right? So we are not very precisely interested in the numerical value of settling time, because we shall just need an idea about the speed of the response. Therefore, we make certain approximations. What is value of zeta for underdamped systems? Between 0 and 1. If we substitute those extreme values, we find that this numerator is approximately equal to 4. You substitute different numerical values of zeta starting from 0 up to 1. So values change between 3.91 to 4.74. That is, this expression is approximately equal to this thing. How did we define rise time? Rise time is the time required for the response to reach from 10% of its steady state value to 90% of its steady state value. So how we can compute this rise time? For example, substitute C of t equal to 0.1 to determine this time. Again substitute C of t equal to 0.9 to determine this time. The difference between the two times is the rise time. But again, this will complex the things. We make approximations which simplify our job, and so we take the rise time to be equal to the time required for the response to reach from 0% of its value to 100% of its value, right? So of course this rise time is not the same as this rise time. However, both the times will be close to each other, and both give us the same information, that is how fast is the response. So if we make this thing, if we use this definition of rise time, our work is greatly simplified. That is, we shall simply substitute C of t equal to 1, and then rest of the job is quite easy. So t equal to rise time, this is equal to 1, which is equal to this right hand side. 1 is cancelled out with this one. This right hand, this term is equal to 0. We can omit the negative sign, so this term is equal to 0. This term cannot be equal to 0 at finite time. So it means that this term is equal to 0. That is cosine of 1 minus zeta square omega n t. Is that true? So we can again simply rearrange the terms. We are interested in dr, so bring it to the other side, and then sine divided by cosine is 10, right? 10 of 1 minus zeta square into omega n tr, that is equal to 1 minus zeta square over zeta. And what is tr then?
Rise time.
Yes, we know that rise time is equal to tan inverse of this expression whole divided by. This is the expression for rise time. Clear?